Hello again. This is the third video in a three-part series and perhaps the most fascinating. As we progress throughout the video, we will be linking the mathematics of expanding a polynomial to geometric representations we can easily understand. We know that expanding a binomial corresponds to a single row of Pascal's triangle, but we will soon see how expanding a trinomial corresponds to two-dimensional space, that being a triangle, and expanding a polynomial having four terms corresponds to a three-dimensional space, that being a tetrahedron. But we won't stop there. We will learn how we can envision expanding polynomials with more than four terms. The formulas we will develop will allow us to expand any size polynomial, and the corresponding graphics will foster our creativity. So now it's time to get exposed to some new formulas, ideas, multidimensional shapes, and graphics you may have never seen before. In video 1, we reviewed the binomial theorem, which, if you remember, was as we see here. Or we can easily express these terms using summation notation and state it in a condensed form. And remember, each binomial coefficient was related to an element in the row of Pascal's triangle. For example, if we were expanding the quantity b plus a raised to the fourth power, we would have the expansion we see here. And each coefficient could have been found by using the fourth row of Pascal's triangle, which is 1, 4, 6, 4, 1. Since 4 choose 0 equals 1, 4 choose 1 equals 4, 4 choose 2 equals 6, 4 choose 3 equals 4, and 4 choose 4 equals 1. You might have also noticed that the sum of any row of Pascal's triangle is always a power of 2, since we are expanding a binomial, and bi meaning 2. In the case of b plus a to the fourth power, the sum of the coefficients in row 4 equals 2 to the fourth power, since we are raising a binomial to the fourth power. Thus, expanding a binomial corresponds to one row of numbers from Pascal's triangle. So before we start looking at multidimensional shapes, let's first review some geometry. In geometry, you might have learned that a polytope is a geometric object with flat sides. The types of polytopes we will focus on is a triangle and a regular tetrahedron. You might have also learned that a simplex is the generalization of using a triangle and relating it to higher dimensions. The simplest geometric object is that of a single point. In mathematics, a point has no length, width, or height. Therefore, it's the zero-dimensional object or space. This can be related to raising a monomial to some power. Next, we think of a line as representing the one dimension. A line segment determined by 2 points has no width or height but does have a length. We will think of a row or slice of Pascal's triangle as being related to the first dimensional space. Therefore, raising a binomial to some power is related to the one-dimensional space. If we continue to think along these lines, an object with length and width but no height would be a two-dimensional object. Examples would be a triangle, rectangle, or circle. For our purpose, we'll focus on a triangle. We will soon see that expanding a trinomial corresponds to all the values in the entire triangle, not just one row of the triangle. Therefore, the entire triangle will represent the coefficients needed to expand a trinomial. Then an object with length, width, and height would need to be represented in three-dimensional space. Some examples would be a pyramid, cube, or sphere. Since we are exploring higher dimensions of Pascal's triangle, we will focus on a tetrahedron or a regular pyramid. In fact, we will focus on a regular tetrahedron, which is one where all four faces are equilateral triangles, as we can see here. This entire three-dimensional tetrahedron will be needed for the coefficients when expanding a polynomial having four terms. Before we continue, let's examine these ideas a bit further. We can think of a point as having a single vertex, and we call it the zero simplex. A one simplex has two vertices, and thus related to a line between them. Let's represent this with 2, 1. Meaning two vertices and one edge or line. A two-simplex is a triangle, which has three vertices. Notice it also has three edges and only one face. The face is in two dimensions. Let's represent this with 3, 3, 1. Then comes the 3 simplex, having 4 vertices, 6 edges, 4 faces, and the entire figure lies in 3 dimensions or has one solid. Thus, we have the sequence 4, 6, 4, 1. Notice the equilateral triangle was formed by placing an additional point equal distance from 2 vertices of a line segment, such that all sides of the triangle were equal. A tetrahedron can be formed by placing an additional vertex equal distance from the 3 vertices of an equilateral triangle, such that we form a regular tetrahedron. If we continue, we might think we could place a point in the center of the tetrahedron in such a way that it will be equal distance from the other 4 vertices and connected to all other vertices. This is sometimes called a hypertetrahedron or a 4 simplex and can be used to try and interpret 4-dimensional space, although we might question how useful this is for us to try and imagine. However, in this case, notice we would have 5 vertices, 10 edges, 10 triangular faces, 5 tetrahedrons, those would be solids in 3 space, and 1 4-dimensional object. Thus we have the sequence 5, 10, 10, 5, 1. We can start to see that the number of vertices, line segments between them, faces created, solids created, and so on for each multidimensional simplex corresponds to a row of Pascal's triangle. What if we extrapolated these properties to higher dimensional simplexes? For example, even though we would most likely fail miserably trying to imagine a 5-dimensional space, since we live in our 3-dimensional world, a 5 simplex would have 6 vertices, 15 line segments, 20 faces in 2 dimensions, 15 solids, 6 4-dimensional objects, and 1 5-dimensional object. Thus the sequence 6, 15, 20, 15, 6, and 1. As the number of terms in the polynomial increase, we end up with increasing dimensional figures. Considering the way humans perceive our 3-dimensional universe, these figures are really quite impossible to conceptualize. For example, we would need a 4-dimensional figure to represent raising d plus c plus b plus a to any power, and you would need a 5-dimensional figure to expand a polynomial of 5 terms. Unfortunately, once we get beyond expanding a trinomial, and especially a polynomial of 4 terms, typically the idea of hypertetrahedrons are usually introduced, if a geometric interpretation is attempted at all. This is really of no practical use to our 3-dimensional thinking minds. Luckily, in this video, we will be exploring a better way we can physically interpret these ideas. We will first explore some interesting graphics and then develop a generalized formula for expanding polynomials. When creating Pascal's triangle, recall that an element in any row was just the sum of the 2 values directly above it. Now let's create what we call Pascal's pyramid or Pascal's tetrahedron. We will label the cap of the pyramid as level 0, just as we did with Pascal's triangle. Level 1, we have 3 ones, and as we add levels of the tetrahedron, each number in the following levels is the sum of the numbers above it, as we can see here in this diagram. Now let's take a closer look at a couple of these individual levels of the tetrahedron. Let's pull out level 4 and look at all the numbers making up the 2-dimensional space represented by this entire triangle. All the values in this triangle are the coefficients we need to expand c plus b plus a to the 4th power. In fact, these values in the triangle correspond to the coefficients in the terms we see here. Check out how these terms correspond to the 4th level of the tetrahedron if we arrange them in this pattern. Again, notice we are using the 4th level of the tetrahedron, since we are raising c plus b plus a to the 4th power. And if we looked at the exponents on the variables, for example, the one we see here with 12c b squared a, the exponents always add up to 4, which we would expect. You might also have observed that since we are looking at the 4th level of the tetrahedron, each edge of the triangle is really just the 4th row of Pascal's triangle. Another interesting way we could create level 4, rather than building the previous levels, is to start with the first 4 rows of Pascal's triangle, and then stand row 4 up alongside the triangle, and then we multiply that vertical row by each element in the corresponding row of the original Pascal's triangle, which creates level 4 of the tetrahedron. Remember that Pascal's triangle is a 2-dimensional figure, but to expand a binomial, we only needed a single row to represent the coefficients. Here, our tetrahedron is a 3-dimensional figure, but we only need one level or a 2-dimensional figure to represent the coefficients of expanding a trinomial. In any one specific level or triangle, we still count the row numbers and the entry in any particular row just as we did in Pascal's triangle. For example, the last row in that triangle is row 4, and the 6 we see in row 4 is the second entry in that row because we always start counting from 0. Also, remember that the sum of any row in Pascal's triangle was always a power of 2. You might try adding up the coefficients we see here in the level of the tetrahedron. You will find that they always add up to a power of 3. In fact, the coefficients of level 4 add up to 81, which is just 3 to the 4th power. Here, the 3 corresponds to expanding a trinomial, and the 4 corresponds to raising the trinomial to the 4th power, and therefore the 4th level of the tetrahedron. Now we start to run into problems because when expanding a trinomial, we already have used part of a 3-dimensional tetrahedron to determine the coefficients, and we want to stay away from trying to conceptualize higher dimensions. So we will stay with 3-dimensional tetrahedrons, which we can visualize and understand. Now let's look at how we might create a tetrahedron that would give us the needed coefficients when expanding a polynomial of 4 terms, such as d plus c plus b plus a to the 4th power. In each of our examples, we will stay with raising a polynomial to the 4th power, just to keep everything consistent, since we are exploring these ideas for the first time. What we are going to do is start with the tetrahedron we just created for expanding a trinomial. It has 4 levels to it, since we are taking a trinomial to the 4th power. And rather than try and represent 4-dimensional space, we will once again take row 4 from Pascal's triangle and stand it up alongside this tetrahedron, and multiply each value in that vertical row times each element in the corresponding level of the tetrahedron, creating a new tetrahedron with 4 levels. However, now since we are expanding a polynomial of 4 terms, we need more than just one level of the tetrahedron to give us all the needed coefficients in the expansion. In fact, we need a 3-dimensional space, and thus we need all the values in all the levels of this new tetrahedron, level 0 through level 4. We will have 35 terms in this expansion, and we now have 35 coefficients in all of those levels. This is now much easier for us to imagine and look for additional interesting patterns than trying to think about hypertetrahedrons. We could investigate how level 0 corresponds to d to the 4th power, and the other variables would all just be raised to the 0 power. Level 1 corresponds to all the terms that include d cubed. Level 2 corresponds to all terms having d squared. Level 3 corresponds to all terms having d to the 1st power, and level 4 corresponds to all terms having d to the 0 power. And just as before, if we added up all those coefficients in levels 0 through 4, they would add up to 256, which is just 4 to the 4th power. Remember, we are expanding 4 terms and raising it to the 4th power. Now what about looking at something like e plus d plus c plus b plus a to the 4th power? Here we have 5 terms. This is when things get even more interesting. This expansion will have 70 terms, and there are only 35 terms in the first 4 levels of the tetrahedron. Thus, we need something more than just a single tetrahedron to represent all the coefficients. So we will begin by proceeding as we have done previously. That is, we will use the original tetrahedron we first created. We will once again take row 4 from Pascal's triangle and standing up alongside the tetrahedron, and then multiply as we have done before, creating a new tetrahedron having 4 levels. This creates a tetrahedron having 4 levels to it, but we still only have 35 coefficients. Next, we will take only the first 3 levels of the previous tetrahedron, and we will multiply it by row 3 of Pascal's triangle, creating another tetrahedron having 3 levels. Then we will drop off level 3 of the tetrahedron, leaving a tetrahedron with its bottom level being level 2, and we will multiply this by a vertical row 2 of Pascal's triangle, creating yet another tetrahedron. Continuing, we will drop off another level, and we'll take the tetrahedron 0 through 1 times a vertical row 1 of Pascal's triangle, creating yet another tetrahedron. And finally, we will take level 0 times row 0, creating just what we might think of as the cap of the tetrahedron. Thus, it only has 1 coefficient. Now, we have what we might call a series of tetrahedrons, one with 4 levels having 35 coefficients in all of its levels. One has 3 levels, having 20 more coefficients. One has 2 levels, having 10 more, and one with 1 level, which has 4 more coefficients, and finally, one with just the cap, having 1 more coefficient. Thus, a total of 70 coefficients are represented. In creating this series of tetrahedrons displaying 70 coefficients, remember we started with the original tetrahedron we first created and used it to produce this series of tetrahedrons. However, we still need to make one more adjustment to create the proper coefficients for expanding a polynomial of 5 terms. What we will now do is again take row 4 from Pascal's triangle and lay it alongside this series of tetrahedrons. We will then multiply every value of each tetrahedron by the corresponding element from row 4 of Pascal's triangle. In doing so, we have created a new series of tetrahedrons still having 70 terms. This new series now has all the coefficients we need when expanding e plus d plus c plus b plus a to the 4th power. As before, let's take a brief look at these values. Notice the smallest tetrahedron, which we might just call the cap. It only has 1 coefficient in level 0. It's related to e to the 4th. The next tetrahedron, having level 0 and level 1, corresponds to all terms including e cubed, and so on down the line until we get to the largest tetrahedron, which contains all the coefficients related to e to the 0 power. Thus, the largest tetrahedron is really just the same values as when we were expanding d plus c plus b plus a to the 4th power. So the cap corresponds to d to the 4th, level 1 corresponds to d cubed, and so on as we move down the tetrahedron. From what we have looked at earlier, can you now guess what the sum of all these coefficients would be? That sum would be 625, which is, as we might expect, 5 to the 4th power, representing a polynomial of 5 terms raised to the 4th power. In video 1 of this series, we alluded to some interesting patterns and information that was hidden within Pascal's triangle. These tetrahedrons are also full of such fascinating patterns. Those of you with a curious mind can start to explore and unravel some of those mysteries now. In this video, we just don't have time to address all the things we could explore. However, now that we are not trying to imagine hypertetrahedrons, exploring those interesting patterns will be much easier. In the interest of time, we will stop with what we have created, where we were looking at a geometric representation for a polynomial of 5 terms raised to the 4th power. Remember, it was a series of tetrahedrons, where each one had 1 less level. Possibly, it might even remind you as something like rushing stacking dolls. See if you can now determine how we could visualize all the coefficients using tetrahedrons for expanding a polynomial of 6 terms, such as f plus e plus d plus c plus b plus a to the 4th power, or one of 7 terms. Give it a shot. If I can do it, I know you can too. It's really quite interesting and a great exercise for your mind. So moving forward, even though these ideas are an interesting interpretation of the expansion of a polynomial, just as with Pascal's triangle, it wouldn't really be practical for higher powers. We certainly wouldn't want to think about creating a tetrahedron with 15 levels in it if we were creating something like this. Before we create a generalized formula for expanding polynomials, let's use some variables that will add some meaning to what we were just doing with our tetrahedrons. Let's let k equal the position in any row of a triangle. We'll let r equal the row number in a triangle, l the specific level in any tetrahedron, n the number of levels in a tetrahedron, and m will represent how many tetrahedrons we have. Remember, each one in this case would be one level smaller, or that's where we had the series of tetrahedrons. Remember, for each one of these, we start counting with 0. First, as we know, we have the binomial theorem, which we developed in video 1. Notice here, r and k have the familiar geometric meaning in Pascal's triangle. We're going to use the binomial theorem to look at c plus b plus a to the L power, where L represents which level of the tetrahedron is needed for the coefficients. We will now group b and a together so we can view it as one term, and thus we will be expanding a binomial where the first term is c and the second term is the quantity b plus a. We now have c plus the second term b plus a to the power of L, and applying the binomial theorem, we have what we see here. And notice we already have the expansion for b plus a to the r power above, which we will substitute in, giving this new expression. Or we could write it as we see here. And we know that L choose r times r choose k can be reduced to just L factorial over L minus r factorial, r minus k factorial, and k factorial. So we now have a way of expanding a trinomial, and we will use this formula in our next step. Now let's look at expanding d plus c plus b plus a to the nth power. Remember, here we need all the levels of the tetrahedron to represent the coefficients. So n represents the number of levels needed. Again, we will group the terms so that we can use the binomial theorem. Thus, we will start with d plus the term c plus b plus a, and we will take all of that to the nth power, where we view c plus b plus a as one single term and apply the binomial theorem, which gives us this new expression. And notice we just got done creating the formula for c plus b plus a to the power of L. So let's substitute that in, and we will now have our new expression, which we see here. And of course, once again, when we look at the product of n choose L times L choose R times R choose K, we can write that in this new form or as a fraction. Let's try one more, and I'm sure you'll start to see a pattern. We now want to expand E plus D plus C plus B plus A to the power of m. And here m represents how many tetrahedrons will be required to display all of the coefficients needed. Remember the series of tetrahedrons we looked at earlier? We will once again just use the binomial theorem by grouping the terms such that we have E plus the second term being D plus C plus B plus A, all of that to the power of m, and use the binomial theorem, and we create our new expression. And we just looked at expanding D plus C plus B plus A to the power of n. So we will once again make that substitution, and we have our new formula. Now, of course, we don't want to keep going and have an endless number of variables. In these examples, the variables were related to the geometric spaces we considered earlier, which was a nice feature. However, ultimately, we want to condense all of these ideas into one generalized formula that will allow us to expand any polynomial of any size to any power. Let's look at these formulas we just developed, but we will use only the variables x and r. We will start by looking at the binomial theorem again. If we switch out the variables, we can state the theorem as we see here. And for expanding a trinomial, we would have this formula after switching out the variables. Notice as we look at these, the only question we would need to ask is how many terms are in the polynomial and the index or power we are raising it to. We could simply then enter in the terms of the polynomial. So now let's jump to a generalized formula and then we will look at it in action. For expanding a polynomial, we can now write this generalized formula. And of course, we can express the coefficient as a fraction as we see here. If this formula was used when writing a program, notice again, all we would need to know is n, the number of terms in the polynomial, r, the index of the polynomial, and then we would simply enter in the terms. In doing so, this formula will produce all the terms in the full expansion of a polynomial in an extremely efficient manner. Let's use these to expand d plus c plus b plus a to the fourth power, which we looked at earlier. Remember, it needed all the levels in one single tetrahedron to represent all the coefficients in its 35 terms. If we use the first formula using L, R, K, and in this case, n would equal 4, the formula would look like one of these two forms. If we use the generalized formula only using the two variables, it would look like this. Either way, as part of a program, it quickly kicks out the terms we see here. In fact, the coefficient in the first term comes from the cap of the tetrahedron. The next 3 come from level 1. The next 6 come from level 2. The following 10 come from level 3. And the last 15 come from the fourth level of the tetrahedron. Notice you can tell what level they come from just by looking at the exponent on the first term of the polynomial. In this case, that's d. The exponent of d starts with 4 and decreases 1 as we go down each level in the tetrahedron. And remember from video 2, where we determined that d plus c plus b plus a to the 10th power would have 286 terms in its expansion. Well, now using this formula within a program, we could efficiently display all of those terms. And of course, just as it was with the binomial theorem, we could have a variety of examples. We could do an example taking this polynomial to the fourth power, where we have 2d minus c plus b plus a raised to the fourth power. In this case, we would simply have the expression as we see here, which would kick out the following terms. Well, I hope you've enjoyed this video, as well as the review materials in the first two videos. I would like to give special thanks to my student, Viraj Faria, who is responsible for creating the animation and helped bring life to my ideas and sketches. If you enjoyed this video, I would encourage you to check out his page, where he is developing some great videos to help students learn various topics in mathematics. Here's the link. From both of us, thank you for watching.